So today's class we are going to continue where we left last time, and basically in this class we are going to have an understanding of how we can extend our understanding of vector spaces, finite dimensional vector spaces, and in terms of different bases. For example, if we start in terms of basis and in terms of dimensions. Dimensions are you can have scalar, you can associate a number, a dimension is a number, but it becomes more involved, it becomes more important, or it becomes more helpful. The idea of dimension has a mapping in the geometrical construction of things, how we geometrically visualize things, these bases, more appropriately in 2 and 3 dimensional spaces. And the extended part of is how the lower dimension spaces can be a subset of those higher dimension spaces, and those spaces, how they can be constructed from those linearly independent and linearly dependent constructions of how we define those two things. So if we say what is dimension. So the theorem goes like this: the number of elements in any basis of finite dimensional vector space V is the same in any other basis. So you can have the elements of any basis of finite dimensional vector space be the same in any other basis. So you can have sort of equivalence if there are two sort of bases which may be constructed of those finite, which may be constructed of those vector spaces. So two bases, there can be equivalence of these two bases. And if you read the argument of the thing is that the proof is a slightly maybe refined method in which we should show that if it is true for n and one of the subspecies is composed of n, the another is of m, such that m is less than n. So you can have the proof is similar to the proof which has been previously constructed here. So I will not repeat it. Maybe theorem, the set of non-zero vectors in the linear combination part of it. So for example, if we have two vector spaces, for example, if there is one, you can construct this xi minus 1, then it is xi, then it's xi plus 1, and xn. So if we have two vector spaces composed of two sets, so you can always say that one can be composed in the other, such that there is a possibility of, you will exhaust the possibility of, because if one of them is linearly, so the construction goes like this. So if I just say like this, so if we have two finite set of vectors which with two bases, so what we are going to do, we assume that every vector V is a linear combination of x's. But x's are not linearly independent. X's are not linearly independent. This is one case. And another case, what we are going to see is Y's are linearly independent, but not every vector is a linear combination of them. So in one of the cases, if every vector, so in one of the cases, one x's are not linearly independent, means they are in one base we have a finite linearly dependent vector spaces. In another we have a linearly independent vector spaces. So this linearly independent vector space can be seen that it's embedded in the linearly dependent vector spaces, and the argument goes in the same way and will exhaust the possibility of the previous one. And at the end you can have n can be greater than or equal to m. The linearly independent the subspace which was constructed out of linearly independent subspaces, it will just exhaust the possibility of the vector spaces which was composed of linearly dependent spaces in the same. The argument goes so the other is the definition. Now there comes the definition. The dimension of a finitely dimensional vector space V is the number of elements in the basis. So again, so dimension. So here is the so dimension of finitely finite dimensional vector space V is the number of elements in a basis of V. Now the third is that theorem. Now the theorem comes like this. Again, the argument or the logic of the theorem is similar to the previous one. So every set of, so I'll only read it, every set of n plus 1 vectors in n-dimensional vector space, space V is linearly independent, fine. So it's linearly dependent. Means these scalars alpha 1, alpha 2 is alpha x1, x1, alpha 2, x2, alpha 1 is equivalent to alpha 2 is equivalent to alpha 3 is equivalent to alpha n is equivalent to 0. So in this case, so every set of n plus 1 vectors in n-dimensional space is linearly dependent. Every set of n plus in an n-dimensional vector space, and a set of vectors in V is a basis if and only if it's linearly independent. That's fine. Or alternative and only if every vector in the V is linear combination of the elements of the set. So the argument is every set of n plus 1 vectors in an n-dimensional space, vector space is linearly dependent. Fine. And a set of n vectors in V is a basis. So you can see the argument goes like this. So now the important thing which will continue is you might have heard in your earlier classes about you might be knowing something about isomorphism. Isomorphism is a sort of mapping which so now in these different dual vector spaces, these finite dimensional vector spaces which are constructed out of those bases, and those bases may be constructed out of those linearly independent or linearly dependent vector spaces. So the point is how we can map one vector space vis-a-vis other vector space. So, and whether the mapping is one-to-one, many-one, on-to, which might be known, how we define the rules of mapping, how we define the functions in the general sense. We have function, we have two sets, so how we map the two sets. So whether mapping is one-to-one, many-one, or it's simply one-to-one. So isomorphic is the general mapping. It's a sort of one-to-one mapping, and we are going to have this. Now we are going to have the how we can map two vector spaces one-to-one, sort of one-to-one mapping in these two vector spaces, and the definition is so two vector spaces over the six or isomorphic two vector spaces. Or isomorphic. So if there is a one-to-one correspondence between vectors x of u, so if you define two vector spaces and we have to define isomorphism between them. So two vector spaces are isomorphic two vector spaces. So two vector spaces we can construct u and v. They are isomorphic if there is a one-to-one correspondence between u and v between the vectors x of u and y of v. So these are two elements in the vectors of vectors or the numbers which we associate in a vector space, which obey rules of how we define vector space. So elements or vectors of one vector space and another by another vector space. So they obey this linearity properties. This alpha x1 plus alpha 2 x2 is equal to alpha times t times x1 plus alpha 2 times t times x2. Got the point? So this for a two vector space to be isomorphic, this property should somehow satisfy this linearity properties. Alpha 1 and alpha 2 are scalars into considerations, and this property is the linearity preserving or isomorphic preserving properties between the. So we can define, if we want to define it. So isomorphism, if we want to define it, isomorphism is a one-to-one correspondence that preserves all linear relations. So you can have one space and you can have some another dual space in which you can have these isomorphic preserving property, how we can identify them. So if you have a general number field of n, a field with n dimensions, so in some class n dimensional field, how we can have n, how it can map to n alternately it can be isomorphic to some another field which has these linearly preserving properties. So that's part of another theorem which is there, and the theorem says like this. The theorem says that the theorem is every n-dimensional vector space V over field F is isomorphic to Fn. So it's isomorphic to Fn. So it's isomorphic to Fn. Uh, so, so every n-dimensional vector space V is isomorphic to a field which is composed of n vector fields. So how we can do it? We can have so linearly preserving property. For example, if we have the proof is very simple. You have a basis in V. So each x in V can be written in terms of one. You can also write it as zeta 1, x1, zeta 1, zeta 2, zeta 3 are the scalars. You can write it x2, so on and so forth. Zeta and xn. And you know that zeta 1 in a linearly dependent vector spaces, this scalar is dependent upon how the different values of these x's. So such that we can have, if we want to consider a correspondence, zeta 1, zeta 2, we can have between V and Fn. So now we have defined x in one vector space. Now if you define them in terms of y, it will be, if we have one set of scalars, because these are two, we are defining isomorphisms by that linearity properties. How we can define vector space in one and related with one, preserving that linearity property. One is u, another is v. If one of the scalars is zeta, you can have another scalars as neta. So neta 1, x1 plus so on and so forth, neta n, xn. So what is that? If you remember, alpha x plus beta y. So it's the way we define T, this property. T we define like this. T we define T of alpha x plus beta y is equal to alpha 1 Tx. So this is the linearity preserving property. So what will happen? So if we define alpha x plus beta y, so this means, so alpha, you can again say it, so you can define these alpha. In turn, is composed of alpha. It's internally composed of x1, x2, xn, so on and so forth. So it's alpha x, alpha zeta 1, because x is dependent upon, if you say this scalar, beta, neta 1, x1, so on and so forth, zeta n plus beta, neta n, xn, and which established a sort of isomorphism. So the point here to mention is so as a part of geometrical statement is normally the isomorphism. So if we assign these vector spaces with some geometrical sensibility, that there is a line, there is a plane. So two vector spaces lying in the same plane from a given origin, how we can relate them, or on a given plane, or in a given volume. So while we are going to map them, there is some isomorphism, and there is some sort of, I use the word invariant transformation, which gets preserved via this isomorphism. When we relate two vector spaces. So it's not that all of them, these transformations can be isomorphic preservings, and maybe so. All theorems and these definitions are tied to them. So if there is, you can define if they are not isomorphic in the sense the way we have defined it. So lot of definitions, and so it leads to a lot of problems. Which you can the feeling of which you can have once you are actually try to do those examples. If there are not exactly isomorphic, preserving transformation between two vector spaces, and maybe in one vector space is it may be composed of linearly dependent or linearly independent vector space. So if the mapping is not one to one, so what sort of problems are associated with that? So maybe there's one example. For example, if you see the examples, for example, he says the example 4. For example, if two rational vector spaces have the same cardinal number, cardinal, one is the cardinality. Cardinality means how many? Ordinality means order. So order is important. The how many means 2, 3, 4, which the amount is interested in the cardinality. So since vector spaces, whether they are finitely constructed, finitely dimensional vector spaces, which are composed of whether they are linearly independent vectors or independent vectors, and linearly independent vectors are shown to be part of some linearly dependent vectors are shown to be part of some linearly independent vectors are shown to be part of some linearly dependent vectors. The scalars in linearly independent vectors may be the value of them can ultimately come to be 0, which is sort of trivial solution. So for example, if he discusses if two rational vector spaces have the same cardinal number, that's if there is one-to-one corresponds between them, they are isomorphic. So there's a linearity preserving one-to-one mapping between them. That's fine. So a knowledge of basic. So the catch is here. The catch is there here that we have to discuss. For example, if we go to the book, example 4, that if two rational vector spaces. So if two rational vector spaces. So I'll just write it here. So if two rational vector spaces. So a number field which is composed of rational vector spaces, rational numbers. So if two rational vector spaces, that's the point, two rational vector spaces have the same cardinal number, have the same cardinality. Cardinality means the number is same. There are 5 elements in one vector space, there are 5 elements in the another vector space. If there are 6, in the same way. So if they have the same cardinality, what we say, and if there is some if there is a one-one correspondence, so they should be isomorphic, or that linearity preserving property should hold between them. So you have two rational vector spaces, and if they are isomorphic to each other and their cardinality is same, so you have to just have a thinking about it, how we can have that isomorphism and how we can prove that cardinality to it. So its mention is that it's interesting to think about it, at least. Before we can become what I should say familiar or become conversant with the sort of logic, language, and understanding with this which this subject of finite three-dimensional vector spaces expects from us or demands from us. So this is a general statement. So now continuing with that, there is also a discussion about subspecies. Again, so in all of these finite dimensional vector spaces, there is a recurring theme which is there, that any there is a space and there is a subspace. There is a finitely dimensional vector space and there is an infinite. So any subspace is contained in the original space. And you have to see what the mappings between these subspaces are linearity preserving, isomorphic, or how we can, so all sort of things. So the subspaces become important in the sense that, for example, if we have a definition, a non-empty set, subset, M of vector space, V is a subspace, or a linear manifold if along every pair, if along every pair x and y of vectors contained in M. So any combination alpha x plus beta y is also contained in M. So any non-empty subset of M of vector space V is a subspace or a manifold if along every pair x and V of vector contains M. So this is the way how we define a subspace. So if we have any non-empty subset of vector space, so it should be subspace or of an if. So here he has used the word linear manifold. The way manifold is used means the idea of geometry and analysis. So how you can the idea of continuity is there, and the idea of geometry is embedded in this. So if there is because we are not interested in general, we are interested in sort of when we talk of this finitely dimensional vector spaces, basically sort of linear algebra or linear manifold, you can say it that way. So the subspaces can be defined. So if we define a non-empty set vector space, which is subspace of near manifold along every pair of x and y of vector, if it's contained in this, the way we have defined that property here. This is scalar. These two alpha and beta are the scalars, and these are the numbers or vectors which are associated with that number field. So this is a basic definition of how we define a subspace. So we can also interpret subspaces as, for example, generalized lines, planes, and so on and so forth. So that's it. So now the question is, for example, apart from that, a subspace can be an empty subset or an universal set. So what can be? How we can identify a subspace? So it's not a trivial problem. So all spaces cannot be subspaces. So we have to define a first space, which is has how we define a vector space, and it's also an exercise in itself how we can whether a given space is a can qualify as a subspace or not. So not all subspaces are subspaces. Only some subspaces qualify as subspaces, and those subspaces which may be composed of these linearly independent or linearly dependent vector spaces. That's it. So we have to be very conscious of how we define a space and how we define the subspace. And subspace is always embedded in a space, the original space which we have defined. So the constraint is that subspace can never, the elements of subspace can always be found in the original space which we have defined in the first place. And if you have, for example, so and I'll just as an exercise, you can read section 1, 2, and 3. What are the non-trivial cases where a subspace doesn't qualify as a subspace? What are the cases you can construct? So that's an interesting or important exercise. You can do it and at least read it. So now the calculus of subspaces. So the intersection of all any collection of subspaces, so again it's an interesting. So the intersection. So it's a result. It's an intuitive result. You can feel intersection of all collection of subspaces is a subspace. You have defined a subspace. So the point is maybe the subspaces of which those spaces are the subspaces. So those subspaces can also form that set, and the set which you can get out of those subspaces. That subspace is composed that the subspace which is composed of those subspaces of which these subspaces are part. Which sort of you can have a logic of set theory that in the a set which is composed of intersection of different sets, it is subset of the original set, you can say it. So a subspaces of different spaces. If we have intersection of those subspaces, that's what the space is itself a subspace of the space which is which is composed of those intersection of those original spaces from which you have constructed those spaces. You can say the logic is like that. So the theorem 2 is theorem 2, this is theorem 1, theorem, this is also theorem. Theorem 2 says, so if S is any vectors, if S is any set of vectors in a vector space S, V, and if M is subspace spanned by S, then M is seen as a linear combination of the elements of S. It's also in the same way, it's the logic you can read it, it's not now I'll just again I'll end this class with another very maybe which I said the element of the dimensionality becomes very much important, that n plus 1 is and higher dimensional space embeds a lower dimensional space. So how we can see dimension of, not earlier talked of dimensionality of general vector spaces, but now we can even talk of dimensionality of those subspaces. A subspace, a subspace which is composed of whether it's infinitely dimensional vector, linearly independent, composed of linearly independent or linearly independent vectors, a subspace, whether it's then you compare one subspace with the another subspace. So it's not you are comparing space with the one vector space with the higher dimensional vector space. No, you are comparing one subspace with a slightly having a dimension with another subspace higher or lower. That's the thing. So the theorem is a subspace. So the dimension, a subspace M in an n-dimensional vector space V is a vector space of dimension less than or equal to n. So that's it. Again, so n is a very large number you can think of. So you can always have a subspace which is, so it's, the statement seems to be clear, and the proof also, if you read the proof, it's also slightly similar, deceptively simple. If you read the first few sentences, so for example, every set of n plus 1 vectors V is linearly dependent, hence the same is true for M. So if any n plus 1 vectors V is linearly dependent. So same is true for M, then the number of elements. So okay, maybe I'll not read it. So you just see it. The argument is not that tedious, but the only point here to mention is that the deceptively, the simpler proof, it needs more thinking you need to prove this simple result, which seems to be so obvious in that sense. So I'll stop here on this, and next we'll continue accordingly. Thanks.